Good morning, everyone. I'm grateful to be here. The sound of the clock ticking with this many of you in the room is deafening, so I'll endeavor to be informative, maybe, or interesting, or at least brief. We work on all sorts of things that are related to condition-based maintenance and diagnostics for systems and energy scorekeeping, and I was hoping to give you a whirlwind tour of some of the things that go on inside my lab. I was also hoping you would be merciful and let me be provocative, just at least for rhetorical purposes, not to offend particularly, but we have like sort of weird takes on some things, and so at least hopefully they might be stimulating, and I'll let you guys decide whether any of it is interesting to you or not as we go through. An example of the kind of thing we do is shown on this slide. We, generally speaking, are concerned with getting actionable information to people for energy scorekeeping, for activity tracking of your equipment, and for condition-based maintenance while keeping your data secure and private. And the trick with that is that it's really becoming sort of a vexing array of opportunities for how you go about doing that. In other words, there are some wonderful things about the sort of the semiconductor revolution and all the tricks we have for sensing. And then there's some other things I just haven't figured out yet, like whether actually crusting everything in the world with sensors and figuring out how to power it, and then dealing with an enormous raft of data that basically the only thing that's willing to look at it is maybe a computer, if you follow me, to try to make some intelligible sense out of it, doesn't necessarily leave me with my favorite way to try to solve problems. And so we've been, and I'm sorry, I should probably explain this. The point here is that what we look at instead is to install less stuff. So the game plan here is we work, for example, in the electrical world, although we do it in a lot of other places too, and I'll show you in a second, on a device we call a non-intrusive load monitor. The monitor sits at the electric utility service entry of any set of loads that you care about, and strictly for measurements it makes at that aggregate point, it uses signal processing to disaggregate the behavior of all the loads downstream. And what that means is you install very little and hopefully think about it and then maybe learn a lot if things go well. And the other trick is that we've been working on this a very long time, but we're definitely not the only people interested in this, especially now. So major players have gotten into and out of the power monitoring business, for example. And one of the reasons that I think that's happened is because it is often the case that it is good dollars chasing bad pennies of loss, if you follow me. And so what you wind up with is something that really just doesn't pay off ever, to start aggregating huge amounts of power data from AMI meters, for example, on server farms, hasn't exactly paid off for most people. And so the model that we use is a little different. The model now is that at any particular site you're interested in, we store the data and it stays. There's enough computing power now on a deck of cards, as others have been saying this morning, that basically there's never any reason to move it. And what we do more so than worry about a data market is an apps market. In other words, now I'm in a situation where the communication with this device is very similar in some respects to Google Earth. I can show you a year's worth of power data or a microsecond's worth of power data without ever moving huge piles of data. I'm only moving a screenful. When you look at that and see something that interests you, we don't move the data back to analyze it. We send an app up to it to analyze it at your site. And it creates a report that's hopefully actionable, and that again is basically a 2G phone communication to move back and forth. So the concept is to keep the data motions here at a kind of a 2G level, if you follow me, for what you might be interested in doing, and take advantage of the fact that by keeping the data and the processing power at the site, it's as secure as you'd like it to be. In fact, it can have no network interaction at all if it's really a mission critical and highly secure need. And we've done that in all sorts of places. These are examples of places where we've installed these systems. That's a picture, for example, in an electric vehicle, older now, much older, of a dashboard refit that we made that will monitor the inside of that vehicle. We've been in a lot of commercial sites, including places like schools. We've been especially found some traction at mission critical operations like oil refineries, and with people who absolutely have to keep their systems up. And I'll give you an example of that. in a second, but that can be, it is very common, for example, on systems that wind up operating with microgrids inherently. In other words, it's not a new idea for a lot of folks. Microgrids have been on ships forever, basically, and it is extremely important that they operate. Same thing for the Army these days. These are places where we've done installations at forward operating bases with the Army to do power monitoring. And these are places where they're supplied by diesel generators or other means like that. And what happens basically is for in-country forward operations, the cost of fuel can range between $8 and $80 a gallon to deliver it to them in order to figure out what's going on. And that's kind of a hint. In other words, again, good or bad, electricity is cheap. And the fact is that, chasing your leftover plugged-in phone charger may be a useful thing to do, but it's not clear what the world is going to look like by the time people actually care about that penny a year. There are a lot of people in the world, as you know, who have super serious problems where the mission availability of the system is critical to them. And that's a place where monitoring and sensing can become very important. This is an example of an older installation for us on this 270-foot Coast Guard cutter. It's showing our system with a sensor box plugged into one of their main panels. That's an older way to do things, and it kind of highlights one of the things we've been working on that I was going to try to show you, which is the basic fact that access is one of the issues. In other words, being able to get the information that you need so that you can apply the signal processing and think about it at the site for the mission critical folks sometimes is a serious problem. An oil refinery an oil rig, for example, will not shut down power even for the time it takes you to put a sensor on as a retrofit, and we've been working to solve that problem, and I'll show you that in a second. So this is kind of an older look at how we would do things when we have the chance to get into a panel. These are the newer looks that show you, this is the engine room of that ship where there's a display of what we hope is actionable information boiled down from the power monitoring on the main panel of that ship, and I'll show you more of that in a second. How does it work? So the plan is that when you start to look at the data at the aggregate point, what you see is things like this. So these are pictures of current versus time for the startup of a personal computer and an induction motor pump. And I won't drag you through all the engineering models of these things other than to say the fairly obvious point, I think, from looking at it, that they're different. And that is wonderful because it means they're fingerprints of what's going on. In other words, this distorted current is an example of what happens for an inexpensive power electronic interface. You notice it's not quite sinusoidal, it's got sort of a spiky shape. And you can see the computer doing its thing. It turns on, and about 1/10 of a second in, that jump up is it's spinning up the hard drives. So it's drawing more power in order to do that. And you can unravel what's going on in this situation and distinguish that, for example, from the case of the induction motor pump, where what you're seeing is a huge slug of current gets drawn while the thing is accelerating the rotor, and then it settles down to steady operation in order to keep pumping water. We don't look at those things directly. So we wind up generating fingerprints of them. So this is a case where, again, we're looking at current versus time for that induction motor pump. And these are the envelopes or signatures of interesting features of that waveform compared with the X's waveform. Those are kind of the fingerprints that the box learns. So we teach the box to recognize these shapes and then have developed algorithms that will find those shapes even when lots of things are happening at the same time. So even if a bunch of things are turning on and off and we've got a mix of things going on, we'll look at that to be able to find that shape in sort of the mess, if you follow me. And we've developed techniques for being able to look from pretty far away. So in other words, the plan here is, this is kind of the telephoto view of the trees on the mountain if you're really close to the load. And this is the wide angle view back further in the power stream if you happen to be looking at the collection of loads in aggregate. And if you're close, you see nice things. And if you're far, as you'd expect, you sort of lose the details of the leaves, if you see what I'm saying. And we're able to recover that. So we've developed mechanisms for being able to look close or far and seeing almost essentially the same thing, basically, as we start to look at these things. And that goes on in anything that uses basically any utility. It's not even just electricity. This is an example, though, from a vehicle. So in a vehicle, what you're looking at is current versus time for a turn signal. So this is left, 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 and it completes the turn, if you follow me. This is an example of it running its windshield wipers for a second. And again, it's a signature that you can find and use, if you follow me, so that you don't wind up needing a sensor for everything on this device. You wind up looking at the whole thing and finding what you're interested in. The access problem is what I was going to tell you about next. So the trick lately that we've been working on is to try to be able to get this information without having to disturb anyone. And I'm referring to myself here with an idiot being able to install the thing. In other words, no custom electrician, no fancy work in order to get the thing on. And one of the tricks to that is sort of thinking about the physics around some of the access problems. So a typical electrical cable, for example, is a null. It has as much current coming up as it does going back, and the net, anytime you look at the fields around it, is a 0. Makes sense, I think. In other words, it's got current out, current back. That's how circuits work. And if you're far away from it, there's nothing. So the usual plan to get data off these things is invasive. You have to go in, you have to separate the wires, you have to put sensors around each of those things, and then start making measurements. But you can get in close to the thing and find the small fields that happen to exist from the close plus minus multipole solutions. And these are just to convince you I'm a nerd. We make circuits to go after those fields and then wind up developing things that look like this. So we call this an electronic stethoscope. It's something that, as I said, and was our first prototype, any fool basically, and I'm referring to me there, can basically grab a wire's outer insulation, never mess with anything that's galvanic or dangerous, and start to pick up both the voltage and the current data from this in order to make the measurements. We play the same game with water and gas and oil. So in other words, the typical water meter in your home, for example, is a fascinating device that's basically a totalizer. It is not, as opposed to this large blue thing over here, a flow meter. The totalizer really just tells you how much got used, if you follow me. But it turns out the construction of that totalizer is fascinating. The way it works is that there's a positive displacement cup in the bottom, and as it spins, it turns a gear in the top, and I always thought that would be shaft connected. It turns out that it is not. They want these things to last forever. So the game plan with these things is that the positive displacement cup that's down here in the brass part spins a magnet. And that magnet winds up grabbing another magnet that's in the gearbox on the top with the needle meter movement. And it basically makes that chemistry experiment you might have seen where, if you remember back to putting a beaker on a hot plate and throwing that white tablet in, and it spins around because a magnetic field grabs it. That's basically how the construction of this thing works. That's fabulous because outside the thing are very small magnetic fields. They're on the order of the Earth's magnetic field. It's very tiny stuff to find. But that's where we bring our nerd to it to look at it with circuits and devices that will let you follow those incredibly small things. And when you do that, you create this. So there's a retrofit that will just, again, I'm referring to me here, an idiot can install, that is just a collar, goes over the existing thing. It doesn't involve a plumber or anybody messing with anything weird or doing something odd. And that retrofit will sense those tiny magnetic fields, and that's what you're seeing in this graph. It's coming out of it, is the light traces are the oscillation of that north-south magnet going around. We extract the envelope of that flow from that oscillation. And what you see is the kind of heavier blue line. And so this, for example, is toilet flush, shower turning on as it fills the head of that. You can find each of those things and again, go after them with a signature the exact same way you can with the electrical monitoring. What that means is that you can now sort of for one-stop shopping in a machine room or a basement or any plant where you have something critical going on, now start to think about putting together a package that with very little installation effort gives you a coordinated picture of the electrical consumption, the water consumption. We can play the same thing for gas and for other fluid flows, if that makes any sense, and start to get all that information. And I'll show you what happens with that. So this, for example, are the power traces versus time for an Army forward operating base. And there are 6 traces on this one because they actually have 2 main panels. So we're plotting both of them. So there's kind of a lot on here. What happens, when you set up a system like I just showed you, so we would come to the site, install the sensors on any convenient place, there's a power cable, and start collecting this kind of information. What does it mean? When you look in on it, we're able to train the box. So if you zoom in on that, and I said it's a little bit like Google Earth, you can keep rolling in on that until you see the rooftop of something, or roll out until you see a whole city or a country basically on the map. And what's lovely about that, again, is all we're ever exchanging, so this can be anywhere in the world, is a screen full of information. In other words, as fast as Google Earth will update that, I can do the same game if you follow me. And then the beautiful thing is, in situ at the site, it will go through and label all those events for you. So it will recognize with the fingerprints that it's learned what things are happening and give you a coordinated picture of everything that's been going on inside that building. And it'll let you break it out as how much energy is being consumed, whether those pieces of the waveforms are healthy or not. So it can go through and do the kind of the details of that down to things like this. Like this, for example, is the extracted turn on and operation of a MacBook. And you can actually go through all those pieces and find the details of exactly what the computer was doing, if you follow me, for each of the pieces of operation from its power consumption. And I'll show you then, moving out a little bit, from the access problem to the sort of the actionable information problem. What we're able to do at that point is then take that information and figure out whether the systems are healthy or not. And I'll give you an example. This is a vacuum-assisted waste disposal system on that Coast Guard cutter I showed you. The vacuum pumps pull a suction on this, and then it's like an airplane toilet. It sort of sucks in the black water from all over the ship, if you follow me, the same way an airplane head works. And it clogs occasionally, so it's got problems. And when it has problems, it may sound silly because I'm talking about the toilet, but it's a mission cripple on the ship. If that system goes down, it's in the main engineering space and it's a disaster. When that clog happens, it's a very difficult thing to find. So in other words, a watchstander who's walking by as that incipient clog happens will see the system running, the vacuum will be being pulled, sinks and disposals will be running just fine. The problem is the controller can't tell what the pressure is inside the receiver tank, so it runs those vacuum pumps until the pressure in there is down to the surface of the moon, basically, before it knows to turn off. And that's very annoying because it means even a dedicated watchstander is going to walk by, hear the vac pumps running, see the system operating, check the clipboard, and assume everything is cool. And it's a general point about closed-loop feedback systems. They're a disaster for energy consumption and condition-based maintenance. Closed-loop feedback controls that, for example, maintain the temperature of this room. Wonderful for us, because we're 72 and happy. But you have no idea right now if half the refrigerant's gone, a fan belt is slipping, and a million other things are going on. And that controller is just flaying that system alive in order to keep us comfortable in here. And it will wear, the Coast Guard, for example, will be able to wear a 30-year system in 6 weeks, basically, if that's not caught. The wonderful thing is you can't hide from the energy consumption. So these are the power traces versus time that show you normal operation, and then the extended runs as the thing clogs. On any given day, it's meaningless. It's random, depends how many people are on the ship, what's running. But it's an easy thing to track and trend, the run time versus the time of the cruise, and develop something that's very crisp to email, basically, the engineering officer. He never has to play with the data. He gets an email in the morning that shows him what's up. And I'll show you another example of that. This was one of the recent happy things that we were able to catch, which was on their main propulsion engine, they have jacket water heaters that fail. When they fail, they're in a heavy vibration and heat environment. They can fail spectacularly and basically cause an engine room fire. We're able to find that. So that screen that I showed you installed on the Coast Guard cutter now runs an item we call dashboard. Dashboard basically pulls out the metrics that I was just showing you and then tells you as progressive problems happen whether the thing is breaking or not. And so the crew gets a continuous readout from us, and this basically prevented what we think would have been an engine fire in December, for example. It's kind of a happy thing. And the last thing I'll close on is sometimes the problems don't fall into one of the bins I've been showing you, and then we still work to try to put together all the circuits and physics to create something that lets us get a non-intrusive look. This sensor is called Vampire, Vibration Assessment Monitoring Point with Integrated Recovery of Energy. And its job is it goes in at the terminal box of a motor, so it is a retrofit. It's not an impossible one, but yes, you have to take the cover off and put this in. It powers itself from the magnetic fields around the motor. It watches the currents and knows when the motor turns off. And it watches the electrostatic system and can tell the speed of the machine, even when it's off, which may sound silly, but if you think about it, the machine does a wonderful thing for you that we almost never exploit. When it turns off, it basically becomes its own network analyzer. So as it spins down, it's going, yeah, and it takes it through a full sweep of the speeds that lets you probe the mechanical system. And that is awesome because it's a time we almost never look at the machines, if you follow me, but it's an incredibly information-rich time. And so this sensor package also includes a vibration sensor, and it lets us, over the course of a set of operations on a ship like this, for example, monitoring this ventilation fan for the crew space, various things will fail. So the rubber mounts, for example, on this duct can fail. The fan can get clogged with crapola and it can become imbalanced and start to ruin itself. That is awesome for us because what happens is we're able to use that Vampire sensor node all in the motor terminal box, never having to move the data, to generate these pictures. So what happens is we can get a transfer function of rotation frequency as it spins down. So 60 hertz would be normal operation, and then as it goes, it turns off. This is the vibration normalized against speed. So essentially it's the vibration divided by the kinetic energy in the machine. Blue would be normal. So what you see is it goes through a resonance, as all mechanical things do. Like if you ever turn off a lawnmower and it goes, and chug, 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 and then stops. That kind of bump is that resonance. When the system is imbalanced like this, you wind up increasing the energy everywhere. And if we track that, we can notice that the thing is starting to become fouled. If, on the other hand, these mounts are starting to fail, that changes the spring stiffness of the mount and it moves the resonance to another place. This little device, the Vampire thing, will report that back out to a non-intrusive load monitor and let us keep track of these things. That's a good place for me to stop probably, but that's a quick overview of some of the kinds of things that we're looking at in the lab to bring information that hopefully is useful to people. Thank you.
Thank you so much, Professor David, Professor Leeb. We can have time for maybe one question. Great.
What's the workload involved in capturing all these? Because you're talking about hundreds of devices, about thousands of devices even on just on the ship.
No, that's the awesome thing, my brother. That's what I'm telling you, is we're not. We're talking about 5 devices, maybe 2. So in other words, the point is the non-intrusive load monitor goes in on one panel. It's got all the loads on it. I have 20 loads now in the engine room. The water wolf, the thing that watches flow, one of those goes on their HVAC or cooling water system, and I've got the five refrigerating units. And then the Vampire unit, sure, for each of those, anywhere it's mission critical, but on the other hand, the number of motors where you absolutely need that, in their operation might be a number like 5 or 10.
How do you know like the feature of a macro turning on, for example?
Oh, you learn it. So in other words, when you install the thing, there are a million things to do. I can either train it in the lab, or I can train it in situ. So in other words, if they'll let me, I'll walk around and turn things on once. If they won't, then there's a commissioning period. It'll sit for a few days, and then we'll figure it out with it. And then when it's trained, it's locked and loaded. Sorry, go ahead. Yeah, sure.
How much complexity can you resolve? So how many devices, signatures can you separate
Yeah.
now? And if you look to the future, what would it take until that number is so high you can manage very large systems with one of these central devices?
Well, no, that's the funny thing. In other words, there is a sanity limit to it. People ask me that, like, so dude, I can put this on at the nuclear power plant and know all of what Springfield is doing if you follow me. And the answer is no, probably never, right? In other words, there's an information theoretic issue there, which is that at some point, your combinations wind up potentially looking like something else, and it's just hash at some number. And there's not necessarily, it's an ad hoc thing. There's not necessarily a particular number that I can tell you. In a home, for example, the number of loads I might be able to get this way could be hundreds. And the reason is because the rate of event generation is low. You wander around the house, basically even if 5 people in the house, they just don't turn that many things on all that often. And so 200 loads, I may get a really good picture of nearly all of them, if you follow me, in that time. In a manufacturing plant, on the other hand, if it's like screw machine machines and they're standing and bam, 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 and then it's as far as the eye can see, you're much less likely to be able to tell anything intelligible for a 50 machine manufacturing plant. It's much more likely that you're on sections of the bus bar looking at 2 of those or 5 of them or something like that. Is informal answer.
Great.
Cool.
Thank you so
Thank
much.
you. You bet. Have fun.
Right.
Yep. Thanks.
Great.